RNA primase. RNA primase lays down RNA nucleotides to make a primer. This is what provides a free 3' hydroxy end for DNA synthesis to occur. So now, let's just stop for a second and let's just make sure that we understand that in order for DNA polymerase, which we haven't really gotten to yet, but DNA polymerase is this one right here. This is the one that really makes the new strand of DNA. In order for this enzyme to be able to even start making a new DNA strand, it needs to begin from wherever there is a 3' hydroxy end. It cannot begin synthesizing out of thin air, okay? It needs to grab a hold of something. Now, on the other hand, primase is able to actually lay those nucleotides on thin air. It doesn't need to get a hold of anything in order to do that. That is the reason why we have primase. Primase comes along, it puts in a little bit, only a tiny little bit, of nucleotides so that DNA polymerase can then grab a hold of that empty 3' end and begin synthesizing DNA from there. Primase moves towards the replication fork on the leading strand and away from the fork on the lagging strand. We're gonna see this movement right now. So here, this is primase and it begins laying nucleotides from nowhere, really. It doesn't need to grab a hold of anything. It is moving towards the replication fork, which already tells us that this strand is the leading strand. Now, after this, DNA polymerase can get a hold of that empty 3' end and begin synthesizing DNA, moving all the while with the replication fork. So DNA polymerase is the one that adds DNA nucleotides to the template strand to form the new complementary strand of DNA. The leading strand nucleotides are continuously added in the 5' to the 3' direction toward the replication fork. So as the DNA is unwinding, DNA polymerase is following right behind, synthesizing the new DNA strand. But this is only for the leading strand, right? Remember that there's also the lagging strand. Here, nucleotides are not added continuously, and that is again the reason for this is only that DNA can only be synthesized from the 5' to the 3' direction. And that is the reason why DNA polymerase needs to wait for the replication fork to open up a little bit more so that primase can come in when there is enough space, lay a primer, and then once primase is out of the way, DNA polymerase attaches to the 3' end of that primer and begins synthesizing away from the replication fork. Because away from the replication fork is the 5' to 3' direction. DNA template runs 3' to 5' from the replication fork, and since DNA is made 5' to 3', fragments of DNA are made, known as Okazaki fragments. So this happens over and over again. You do one fragment at a time, one fragment at a time, and these fragments are what we call Okazaki fragments. Here we have the leading strand. This one's easy to follow. See, we're synthesizing from the 5' to 3' end, meaning that this primer had a 3' hydroxy empty, and it goes on and on and on it goes. It doesn't stop until the replication fork stops. And that doesn't happen until it meets another replication bubble or it meets the end of the chromosome. Now the lagging strand, we have a primer here. So primase already came in and put in its RNA primer. Now, DNA polymerase, which is the same one that we were looking at just before, comes in and fills in the gap. Notice how this could be a loop that goes on and on and on and on. See, this could be like a second fragment being filled. Now primase needs to come in and put in, primase already came in and put in a new primer. And DNA polymerase comes again and it does it over again. It fills in the gap from primer to primer. Then primase needs to come in again, put in another primer. Okay, it's done doing that. DNA polymerase comes in again and it fills in the gap. And this happens over and over again as long as the replication fork keeps going there to the left. See? Now this is where primase came in again to lay a new primer. DNA polymerase comes back, fills in the gap, and then we need primase to come in again and put in another fragment or another primer so that DNA polymerase can grab onto it and begin synthesizing DNA. And it goes over and over again. So DNA polymerase removes the RNA primer as well, nucleotides from the strand, and replaces them with DNA nucleotides. This is another type of DNA polymerase, to be sure, but this type of DNA polymerase, this orange one that you see here on the image, removes the primer and it replaces it with DNA. Fills in the gaps between the Okizaki fragments with DNA nucleotides but does not connect the fragments. That is the work of another enzyme. This enzyme also has proofreading ability to check for any errors in base pairings. So here, this is actually showing the correction, okay? Or not really the correction, but the elimination of the primer with what we call an exonuclease. Now, I said correction because I know from taking genetics that an exonuclease is also the same enzyme that we use for making corrections. When this type of DNA polymerase detects that there is a mismatch from one, for example, a mismatch would be if DNA polymerase connects or tries to connect thymine with cytosine, for example. We know thymine goes with adenine, but if thymine connects or attempts to connect with cytosine or guanine, that is a mismatch. And then an exonuclease would come in and take out that nucleotide to replace it with the right one. But here, exonuclease is also doing another of its jobs, which is removing the RNA primer so that DNA polymerase can continue and fill in that little gap. Now, DNA ligase is what is actually going to connect them. Notice how here, when DNA polymerase fills in the gap, there is still a little portion left over there. It's not completely closed. That is what ligase does. It ligates the Okazaki fragments together in order to form a continuous complementary strand. And again, this is something, ligase is an enzyme that would only have a job at the lagging strand. It creates a covalent bond between a 5' phosphate and a 3' hydroxy of adjacent nucleotides. It does not add any new nucleotides. It only connects the 5' phosphate with the 3' hydroxy. And that is DNA ligase. Simply closing the Okizaki fragments. And we've reached the end of DNA replication and the genetic code. This is also the end of Lifeline. It has really been a pleasure to help you through lecture this semester. And I will continue to be your Lifeline leader throughout the rest of the semester. So, any questions that you have, feel free to post them on the discussion board. And that way, everyone else can see what you asked, and everyone else will be able to see the answer that I gave you. Hopefully, that's going to help for the final. Have a good day, everyone.